Okay, ladies and gentlemen, this is the part of the gases unit where I'm going to be talking to you about how to do molecular weight calculations from the ideal gas law from PV equals nRT information. It's fairly straightforward, but I think that it can be a little challenging if you haven't seen it before. So if you can get this simply by reading the chapter, that's fine, but I think that this lecture video might be helpful for most of us. So essentially, I'm now talking about questions where they give you information about the gas and then they ask you to calculate the gas's molecular weight. And there is no formula given, so you can't simply add up the individual atomic masses from each of the elements because you don't have a formula. So remember that molecular weight is grams per mole. Molecular weight is gram formula mass, is molecular mass, it's molar mass. We've got like 15 different names for it in chemistry, and they all mean the same thing. Number of grams per mole. Molecular weight is grams per mole. We're used to seeing this as a unit, but this is also a mathematical function. This is saying if you have grams and you have moles and you divide the two, grams divided by moles, you get molecular weight. You get molar mass. And that's the idea behind these calculations. Get mass, get moles, divide the two, kaplam, you got molecular weight. You've answered the question. So in terms of PV equals nRT, if we think about mass and we think about moles, which one of these two things that we need to divide in order to get to molecular weight is also in the ideal gas law? And the answer should be moles, right? Moles. We have moles in both of them. We have moles here and we have moles here. So moles are the calculations that we should be doing with the ideal gas law. So the strategy in these molecular weight problems is simply going to be to use gas information, pressure, volume, temperature, etc., to calculate moles of a gas. And then once you have moles of a gas, then you go back to your problem. I'm going to bet you that they gave you the mass of the gas in that problem, or some way to get it, some sort of lab information where you can maybe just need to subtract the mass of the empty container, but I bet you have mass information about that gas there, and then you simply divide the two to get molecular weight. So sample problem. Calculate the molar mass of a gas if 2.5 grams occupies 0.875 liters at 685 torr at 35 degrees Celsius. Well, molecular weight, they're looking for the molar mass. That means molecular weight. That's grams divided by moles. Which one of these values has the problem already supplied us with? If you read this through, calculate the molar mass of a gas of 2.5 grams. 2.5 grams, right? They have given us the mass. We already know the mass, which means that all we need to do is calculate moles, and we will have all the information we need in order to get molecular weight. So we're going to do, if we look at the other information we have volume, we have pressure, and we have temperature, which means that we have everything we need to do a PV equals nRT problem. But before we jump into PV equals nRT, there are a few conversions that need to be made. Now, Mrs. Julian is desperately old school, and whenever she does PV equals nRT problems, she will always put the pressure in atmospheres. You kids today and your multiple values for R based on different units for pressure. By sheer principle, I only ever ethically believe in using the 0.0821 liter atmospheres per mole Kelvin. To me, that is the value for R. None of this nonsensical 62.36 whatchamacallits. No, to me that number's bogus. So on principle, I will convert all of my pressures into atmospheres before using them in PV equals nRT. You can laugh if you like, but for 100 years, this is what chemists did, and I'm not going to spit in their face. So 685 torr, I want to get it into atmospheres. And by now, hopefully you feel very comfortable that we're going to do 760 torr on the bottom and 1 atmosphere on the top. You have to be able to do conversions like this, like clockwork. These are the big conversions in gas chemistry. Do this out, we get 0.901 atmospheres. But we also have to convert the pressure. We can't put a negative value. We have to use the Kelvin scale when we're dealing with gases, any calculation involving gases, because it's the scale of temperature that doesn't have negatives. We can't put a negative value for T into this equation because then we'd be talking about negative values for moles, negative values for pressure, negative values for volume, and those things don't exist. So we've got our 35 degrees Celsius. To convert that to Kelvin, we're going to add 273. So we get a value for temperature of 308 Kelvin. Now that everything is in its proper units, we can go ahead and use PV equals nRT. So pressure, 0.901 atmospheres. Volume, it's in liters already. Has to be in liters, 875 liters, equals, I'm just going to drop down here, N times 0.0821 liter atmospheres per mole Kelvin. And then the temperature, as we said, 308 Kelvin. And then this is simple arithmetic, right? You're just dividing out. I do want you to actually do this math. It's important that you, if you're following along, that you're making sure that you're getting the same answer that I am so that you know that you can do this math correctly. When I do this, I get a value for N of 0.0312 moles. That's good, but that's not our answer because remember, the whole reason that we're calculating moles is to take it back to the molecular weight equation. Molecular weight is grams per mole. It's mass divided by moles. So now, to figure out the molar mass of this gas, we're going to do the mass, which was again given in the problem, 2.5 grams. We had that number the whole time, and we just had to calculate the moles of the gas, 0.0312 moles. Mass divided by moles is molecular weight. Grams per mole. This is what unit this math will get you. Do that math out, 2.5 grams divided by 0.0312 moles. You get a molar mass of 80.1 grams per mole. So molar mass using PV equals nRT. Again, the idea is that PV equals nRT is going to get us moles, and then the problem 9 times out of 10 will have the mass already in there. If it doesn't have the mass in there directly, we can usually calculate it through some simple subtracting away the mass of the empty container thing and get the mass that way, and then do mass divided by moles for molar mass. And that's all there is to the molecular weight from PV equals nRT. Try the sample problem in the packet on your own.